Hello friends, in this video today we are going to discuss about orthogonal system, Hermitian operator and properties of Hermitian operator. So first let us start with orthogonal system. Now let us consider two wave functions psi1 and psi2. And psi2 star is complex conjugate of psi2 such that product integrals product integral tends to 0 in a definite interval x greater than equal to a less than equal to b. So that means if integration from a to b of psi2 star psi1 dx is equal to 0, then these two functions are said to be mutually orthogonal. Then psi1 and let me clean this first. Psi1 and psi2 are said to be mutually orthogonal. So hope you have understood this orthogonal condition. So now let us discuss about Hermitian operator. Now here you see, let me mention one more thing. These two functions psi1 and psi2, these are functions of x. Psi1 and psi2, these are functions of x. Remember that in this case. Okay, so now let us discuss about Hermitian operator. What is Hermitian operator? An operator, suppose p cap is said to be Hermitian operator if integration psi star p cap psi dx is equal to integration p cap operates on psi and whole star psi dx. If this p cap satisfies this condition, then it is said to be Hermitian operator. And remember, this psi is a normalizable wave function, and it is normalizable. It is function of x. Okay, it is function of x and it is normalizable. Remember that. Now here you see one more thing. Suppose we have two functions psi1 and psi2. Suppose psi1 and psi2 are two normalizable wave functions. Such that psi is equal to psi 1 plus psi 2. Okay, then our normalization can be our this condition to be this operator to be Hermitian, the condition will be such that integration psi 1 star p cap psi 2 d tau integration p cap star psi 1 star psi 2 d tau. That is the normalization condition for this operator to be Hermitian, right? So hope you have understood this. Now let us discuss the properties of this Hermitian operator. So this is the first property of Hermitian operator. Hermitian operator have real eigenvalues, right? Real eigenvalues. So now here you see, in order to prove this property, let us consider, let lambda be an eigenvalue of Hermitian operator in the state Hermitian operator, suppose p cap, in the state described by a normalized wave function described by a normalized wave function. Let me write it clearly. Wave function be psi, then eigenvalue equation will be given by the eigenvalue equation is given by p cap psi is equal to lambda psi. This is suppose equation number 1. Now if we take complex conjugate on both sides, taking complex conjugate on both sides, then what we will get? P cap star psi star lambda star, then again psi star. This is suppose equation number 2, right? Now here you see, according to Hermitian condition, Hermitian operator, according to the condition to be an Hermitian operator, of Hermitian operator, what was the condition that we have discussed earlier? That integration psi star p cap psi d tau is equal to integration p cap star psi star then psi d tau. That was the condition. Now using 1 and 2, use these two equations in this tree. Okay, then what you will get. Now here you see this p cap psi, this p cap psi can be replaced by lambda psi, right, from equation number 1, and this p cap star psi star can be replaced by this. So using 1 and 2 in this equation, what we're gonna have integration psi star lambda psi is equal to lambda psi d tau integration, and if you use 2 here on right hand side, then what you will get, lambda star psi star psi d tau, that's what you will get. So here you see this lambda and lambda star, these are constants, you can take outside of the integration. So let me write here using 1 and 2, using equation number 1 and equation number 2, right? So let me scroll down the page. Okay, so from here what we can do, we can write lambda integration psi star psi d tau and lambda star integration psi star d tau, that's what we can write. Okay, so this implies lambda integration psi star d tau minus lambda star integration psi star psi d tau is equal to 0, and from here you can see, you can take this part common, right, and then what you will get, lambda minus lambda star integration psi star psi d tau is equal to 0. So we know that we have already considered that psi is normalized wave function. Initially we have already considered that normalized wave function psi, right? So what was the normalization condition? We have discussed in, I think, in previous lecture maybe. Okay, normalized condition was psi star psi d tau is equal to 1. This is the normalized condition. So that's why here you see product of these two is equal to 0. That means either this can be 0 or this is equal to 0. So as according to the normalization condition, this cannot be equal to 0, this must be equal to 1. Therefore, since psi star psi d tau is equal to 1, therefore lambda minus lambda star is equal to 0. Then so this lambda must be equal to lambda star. So now here you see lambda star represents complex conjugate of lambda. If lambda is a complex number, suppose a plus ib, then its conjugate should be, lambda star should be a minus ib, right? A minus ib, and these two cannot be equal. Here plus ib, here it is minus ib, and it is possible if and if only this lambda is a real. That means here this b must be equal to 0. Okay, that means if b equals to 0, this imaginary part is equal to 0, that means only we have the real part. So that's why these two lambda was eigenvalue, isn't it? So lambda is a real number, because if it is complex, it cannot be equal to its complex conjugate, right? So lambda is real, which proves that the eigenvalue of its Hermitian operator is real. Thus eigenvalue of its Hermitian operator is real. So hope you have understood. Now let us discuss the second property of the Hermitian operator. Two eigenfunctions, suppose two eigenfunctions of Hermitian operators belonging to different eigenvalues are orthogonal. So what does it mean? It means, suppose we have two eigenfunctions, wave functions, psi1 and psi2, and if p cap is a Hermitian operator and it operates on psi1 and it gives, suppose, lambda 1 as the eigenvalue, and eigenvalue equation is this, and for this wave function psi2, if p operates on psi2, it gives, suppose, lambda 2 psi2. So they are belonging to two different eigenvalues. In that case, this property says that these eigenfunctions are orthogonal. The eigenfunctions of Hermitian operators are orthogonal. So what does it mean? So that means it must satisfy the orthogonal condition. And what was the condition? That is integration psi2 star psi1 d tau equal to 0. So this is the condition. So we need to prove this condition from the, in order to prove this property. So now let us prove this property first. So how to prove that? So here, suppose, let us consider, let p cap be a Hermitian operator and psi1 and psi2 be two wave functions, be two eigenfunctions, suppose, be two eigenfunctions of operator p cap, and lambda 1 and lambda 2 respectively be two distinct corresponding eigenvalues. Then when p cap operates on psi1, it must give lambda 1 psi1, and when p cap operates on psi2, it must give lambda 2 psi2. This pair of equation is, suppose, equation number 1. Let us consider this is equation number 1. Now here you see, let me scroll down the page. Taking complex conjugates of this equation, taking complex conjugates of equation number 1, the pair of equation number 1, then what you will get from the first equation, what we're going to have, p cap star psi1 star is equal to lambda 1 star psi1 star. Then here you see, according to the first property, Hermitian operators has real eigenvalues, isn't it? So this lambda star must be this lambda 1 must be a real. So if lambda is real, then it must be equal to lambda star, we can say, right? So that's why we can write this as lambda 1 is equal to, so it's equal to lambda 1 psi 1 star. Since lambda 1 is real, so lambda 1 must be equal to lambda 1 star, and hence lambda 2 also equal to lambda 2 star, right? Why it is real? Because Hermitian operator has real eigenvalues, isn't it? Hermitian operators have real eigenvalue. That is the reason. So similarly, we will get p cap star psi 2 star lambda 2 star psi 2 star, and lambda 2 star will be again equal to lambda 2, as it is also real. So hope you have understood, and let us consider this pair of equation. Let us consider this pair of equation as equation number 2. As equation number 2. Now, here you see, let me mention one more thing here, as p cap is Hermitian operator. That is why this lambda and lambda 2 are real. So hope you have understood. Let me write it cleanly. Since p cap is Hermitian operator, hence lambda 1 and lambda 2 are real. So lambda 1 must be equal to lambda 1 star, and lambda 2 is equal to lambda 2 star. That is the region. So hope you have understood this. Now, from these two equations, what we can do, according to the condition of Hermitian operator, we have got an condition of Hermitian operator, that is, let me use the reading. Hermitian operator. So what was that? Integration psi 2 star p cap psi 1 d tau is equal to integration p cap star psi 2 star psi 1 d tau, right? So if we use the equation number 1 and 2 here, so here you can see this can be replaced by this, right, from equation number 1, and from equation number 2 what we can do, this can be replaced by this, right? So let's do so. Then what you will get? So let me scroll down a bit. So let us use equation number 1. So let us put these two values, this one and this one, in this equation. So let me, okay. So then if what you will get, psi 2 star, and instead of this let's put lambda 1 size and d tau equal to integration, and instead of p star psi 2 star lambda 2 psi 2 star. Let us put lambda 2 psi 2 star and psi 1 d tau is. So using equation number 1 and equation number 2, so that's what we have used. So hope you have understood this. Now from these two equations what we can do, so here you see this lambda 1 can be taken outside, psi 2 star psi 1 d tau, then on the other side this lambda 2 can be also taken outside. We got it. Now it implies lambda 1 integration psi 2 star psi 1 d tau minus lambda 2 psi 2 star psi 1 d tau. So here you see we can take these two parts common, right? And on the other side we will get 0 here. This part is brought to this side, right? Let me scroll down the page. So now what we get, lambda 1 minus lambda 2 within bracket integration psi 2 star psi 1 d tau is equal to 0. Now here you can see that we have already considered here that these two lambda 1 and lambda 2 are two different eigenvalues. These two are two distinct eigenvalues corresponding to psi 1 and psi 2, right? So that is why if these two are distinct, if they are not equal, if psi 1 is not equal to lambda 1 is not equal to lambda 2, then lambda 1 minus lambda 2 cannot be equal to 0. So that is why here you see if their product of these two part is equal to 0, that means any one of them must be equal to 0. As we have got this is not equal to 0, this psi 1 and psi 2 is not equal to 0, that's why this part must be equal to 0, this part must be equal to 0. So what we're going to write here, since lambda 1 is not equal to lambda 2, so lambda 1 minus lambda 2 is not equal to 0. Therefore psi 2 star psi 1 d tau is equal to 0, which is the condition of orthogonal, right? So which proves the second property, that psi 1 and psi 2 are orthogonal functions. Thus psi 1 and psi 2 are orthogonal function. Hence proved, right? Now let us discuss the next property. So our next property is, if two Hermitian operator commute, then their product is also Hermitian operator. So you know the meaning of commute. Suppose we have two numbers, 2 into 3, that's 6. 3 2 is also 6. In both cases we are getting the same result. That means they commute under multiplication, right? So hope you know this basics thing. So here you see, suppose we have two wave functions, lambda 1 and lambda 2. So let me write here proof. So what we need to prove here, if these two are functions, let me write be two wave functions, and A cap and B cap be two Hermitian operators such that A cap B cap as they commute, so we can write A cap b cap. We can consider we have considered two Hermitian operator, they commute. Okay, a cap b cap is equal to b cap a cap, such that a cap b cap equal to b cap a cap. Okay, now we have to show that product of these two, product of a cap and b cap, is also Hermitian operator. That we need to prove here. So here you see, let us consider this integral psi 1 star a cap b cap psi 2 d tau. So if a cap is Hermitian, then here you see, consider this group, this is one group, consider this part as one group, then what you will get. So let me write this way, this is equal to psi 1 star a cap b cap psi 2 d tau. Let us consider this way. Then we know the condition of Hermitian operator. What was that? That Hermitian condition for Hermitian operator was such that integration psi 1 star p cap psi 2 d tau is equal to p cap star psi 1 star psi 2, right? Psi 2 d tau. Now here you can see, compare a cap with p cap and compare this one with this, and psi 2 is b cap psi 2. So if you compare this way, then what will be the result according to this? Then our results gonna be equal to integration a cap star psi 1 star then b cap psi 2 d tau. That's going to be our result. So this is suppose equation number 1. So now let us clean this part. Then again, now here you see, if you consider b cap as Hermitian operator in this case, and if you consider this one as one group, then what you will get from this result. Now if b cap is Hermitian operator, then take this integral, then what you will get, take this a cap star psi 1 star as one group. Let us take this one as one group, then b cap psi 2 d tau. So again, applying the Hermitian condition, you're gonna have b cap star then a cap star psi 1 star psi 2, right? You're gonna have this result d tau. So let me write this one clearly, b cap. Okay, so you will get this. This is equation number 2. This is equation number 2, right? Now from equation number 1 and 2, what we can have here, you can see clearly if you compare these two. So this is equal to this one, and this is nothing but taken from this, right? And this is equal to this integral. So we can say these two integrals are equal, right? So from equation number 2 and 1, from 1 and 2, from these two equations, what we have got, let me scroll down the page. So this two implies psi 1 star a cap b cap psi 2 d tau, that's equal to b cap star a cap star psi 1 star psi 2 d tau. That's what we have got, right? So here you see, As we have already considered that a cap b cap commute, right? A cap b cap is equal to b cap a cap. So we can say a cap star b cap star also commute is equal to b cap star a cap star, right? So this is suppose equation number, let me take, this is equation number 3 suppose, and this is suppose equation number 4. If you use the equation number 4 in 3, let me scroll down the page, using 4 in equation number 3, then you get psi 1 star integration psi 1 star a cap b cap is equal to d tau, sorry, psi 2 d tau is equal to, and this b star a star b cap star s a cap star, that can be written as a cap star b cap star, right? As the commute a cap star b cap star psi 1 star psi 2 d tau. That's what you will get. So here you see what we have done. We have replaced this by this result, right? So we have got this. Now here you see, consider this one as one operator, then imagine this and compare with this result, this condition of Hermitian operator. This was the condition for Hermitian operator, right? P cap psi 1 star p cap star psi 1 star. So let me write it properly. P cap star psi 1 star psi 2 d tau. This was the condition. So if you compare that a cap b cap as p cap, and this is psi 1 star and this is psi 2 star, right? This is p cap star, then psi 1 star, and this is psi 2 d tau, right? So it satisfies this condition. So we can say this product a cap b cap is also a Hermitian operator. Therefore, thus we can say thus a cap b cap is also Hermitian operator. Okay, so here you can write, this is Hermitian condition. You can write here, this is Hermitian condition. Okay, that's how we can prove this property. So hope you have understood. Now let us take one question related to this topic. So in this question you can see here, we need to show this momentum operator, this is momentum operator, is Hermitian. So first note that any operator, suppose p cap, is said to be Hermitian if its average value for a state psi is real. So how to find the average value or expectation value, that was discussed in details in first lecture. I will provide the link in the description box. Please watch that video till end before you solve this problem, then you will understand. Okay, so the first lecture was long, but you have to watch that first, because in the first lecture I have explained what is wave function and what is the how to calculate the average value in details. So that's why video may be very long. So though it is long, please watch that video first for better understanding, right? So now let us start. So first let me clean this. So here you see, so momentum operator is generally represented by p cap. So let me write here proof. which is here h cut by I del by del x. So its complex conjugate is p star, that is h cut, and replace this positive I by negative I, then you will get the complex conjugate, right? So expectation value or average value of p cap is nothing but minus infinity to plus infinity psi star h cut by I del by del x del psi by del x, sorry, dx. So that's how we calculate expectation value, right? Now let us consider this psi star as u and this part as v, and now apply this rule. Integration u v dx is equal to u integration of v dx minus integration within bracket derivative of u, that means du by dx integration v dx whole into dx. Let us apply this rule here. If you apply this rule, then let me tell you one more thing. Here v is, we have considered this del psi by del x. If you integrate this, then this part will give you psi only, right? And here also again from this part also you will get psi, and you can write the constant, okay? And this part will remain in, okay, and derivative of u, that u is here in this case u is psi star. So from here we will get del psi star by del x, right? So let's apply this rule. So what you will get, so our result will be h cut by I, then psi star psi minus infinity to plus infinity, we have limits here, minus integration minus infinity to plus infinity, then h cut I. So here we have in this, if you compare this one with this, then what you will get here, integration h cut by I del psi by del x, isn't it? And h cut by I is constant, so here, and integration of del psi by del x is psi simply. And let me write the psi first, then this du by dx, derivative of u is here this psi star, so derivative of psi star del star by del x, you can write this way, and then you can write the psi also. So let us keep this way, dx. So right, we'll get this. And here you see, in this case, if you apply these limits, then this part's gonna be equal to 0, minus infinity to plus infinity if you put here. So this part's gonna be 0 here. Now here you see, as this part's gonna be equal to 0, so we have got minus infinity to plus infinity psi h by I del psi star by del x dx. We have got this, and this can be written, this minus can be written here also, right, in this way, minus infinity to plus infinity psi h by minus I, sorry, let me write properly, h cut by minus I del by del x psi star dx, right? We can write this way. So here you see, this is nothing but, if you see this part is nothing but p cap star, and if you compare with this, and this whole thing is average value of, this whole thing is average value of p cap star, right? So you can write this is nothing but average value of p cap star. So here you see, if average value of p cap and p cap star are equal, that means their average value must be real. Okay, therefore since you can write, since p cap expectation or average value of p cap is equal to that of p cap star, therefore p cap expectation value of p cap is real, and hence the momentum operator p cap, which is equal to h cut by I del by del x, is Hermitian. Right? So that's how we can prove. So hope you have understood. If you have understood, please share with your friends, and if you are new to my channel, subscribe the channel, hit the thumbs up button, and stay connected. So thank you for watching. See you in the next video.